and just wanted to hit a couple of announcements because they are coming closer to fruition. Okay. Not this week, not next week, but the following week. On Wednesday, the 12th, will be the College Transfer Fair Days on the Birmingham campus. That's the Birmingham West campus, the B building, academic building, and it'll be all up and down that hall, I'm pretty sure. They'll have tables set up for a variety of these. Well, he decided to show up. Okay. Christian's here. All right. They said you weren't coming. So there's a bunch of schools that have been invited, and as far as I know, most of them usually do show. Then on Thursday, they'll be here on this campus. This is Thursday, the February 13th, again from 7:30, 9:30 until 11:30. For some reason, my projector decided not to come on. Okay, and then the next one is something I highly encourage this group of students and groups and students like you. So if you know any fellow students who may be pre-engineering majors, there is a great summer research program at the Center for concerning power optimization of electrothermal systems, POETS, and they're looking to recruit specifically minority engineering students to work at 3 of the 4 institutions, University of Illinois, University of Arkansas, and Howard University. It's a 10-week internship, exposes undergraduate students to academic research in fields of mechanical, electrical, and material engineering. Students are paid a $5,000 stipend. Now, if that seems a bit excessive or lucrative or something to you, it should. I take it most of you are pre-engineering students, right? America is hungry for engineering students. They really want you to continue in the engineering field. That's why they can put out this kind of bucks. They want engineers. We need engineers. Right now, we're having to import engineers from India, China, all sorts of other places because we're not producing enough homegrown engineers. Please, folks, stay with it. Consider these opportunities. Take advantage of them. In many situations, when you get into your 4-year degrees, 4-year schools, you'll be able to get. I was down at University of South Alabama last spring, sometime later in the term than this, but they were having what they call an articulation meeting. I thought it was statewide. It was just for them. And boy, to hear their students talk, just about all their students can get some type of assistance to pay almost their entire way through that last 2 years. It is a great field, great opportunity. Hang with it, folks. That's my soapbox. I guess I'll get off of it now. The point here is February 15th, deadline. So if you are interested in this, here's information, there's information, and I've even got a little brochure that I printed off. It's a trifold, but I had to print it on 2 pieces of paper, so don't pay any attention to the middle part, but the outside, or inside I can barely read, but the inside has most of the information in it. Please take advantage of some of these opportunities. They're there for the taking. All right, I think I got everybody here. Enough of the paid political announcement. Let's move on. Okay. Any questions on anything we've done so far? All right. We're in Chapter 2, Limits and Their Properties, 2.3, Evaluating Limits Analytically, which is, to me, the way to go. And example 2, top of page 84, is where we are. Okay? Find this limit. The limit is x approaches 2 of 4x squared plus 3. What would be your first approach to finding that limit? Plug it in, okay? My pen string cord was hiding. Okay, what would that give us? Let me get my pen set up. What would that be? 4 times 2 squared plus 3. What would that be? 19. Perfect. Okay. Any questions about this? Can it get much easier than that? Okay. 19. Okay. Now, that's a polynomial function, right? 4x squared plus 3. Defined for all real numbers, so you didn't have to worry about any x's in the denominators. Polynomials don't have variables in the denominators. You don't have to worry about square roots. Polynomials don't have square roots. They only have integral powers, and square roots are fractional powers. There is no issue with that at all. Plug it in, plug it in. Okay? And I think we can just continue here and show how they did it. And they broke it down into gory detail, and if you need to do this, by all means do it. I see no reason not to just plug it in here. What they did, according to the property 2, theorem 2.2 from the previous page, they broke the addition into the limit of a sum is the sum of the limits, okay? And I have a feeling I know what they'll do next. Then they'll break this into 4 times the limit is x approaches 2 of x squared, plus, and the limit of 3 is x approaching 2 is just 3. So that will become 3. This will become, if you break it down this way, 4 times the limit is x approaches 2 of x squared. That's property 1 of that same theorem. And then, lo and behold, you can probably do one more step if you want to throw it in. Why not just plug it in up there? But if you wanted to, you can, oh no, they do just plug it in there, okay? Limit is 4 times 2 squared plus 3, which is what we went straight to. No problem with that, and that gives you 19. Any questions? You can string it out as far as you want, whatever it takes for you to understand how to do it and what the steps are. Any questions? All right. That leads then to, not only that, that limit is reinforced by the graph of the function shown here, and the limit as x is approaching 2 would then be right up there, okay, 219. You get by just plugging in. That was really beneficial to see that, I'm sure. So, any questions? All right. The limit as x approaches 2 of a polynomial function, p of x is equal to this is what I would say, is simply the value of that polynomial function at the value x equal 2. So all you have to do is plug it in. There's no reason to string it out unless you see it better that way. This direct substitution property is valid for all polynomial and rational functions. The problem with rational functions, though, is a ratio of 2 polynomial functions. Polynomial functions typically have x's in them. Numerators find that denominator, any value for x or the independent variable in the denominator that would make that denominator 0 can't go there. Okay? So that would be all rational functions with non-zero denominators. Okay. Make sense? Questions? Okay. That lends itself to theorem 2.3, limits of polynomial and rational functions. We'll start with the polynomial. If p is a polynomial function and c is any real number in the world, then the limit as as x approaches c of p of x, plug it in. Okay, plug in the c for the x, and you've got the answer. That works for every polynomial function every time. However, if r is a rational function, not a polynomial function, and this rational function is a ratio of p to q. P of x is a polynomial function, q of x is a polynomial function. Both of these functions are good wherever, whatever x you put in, and C is any real number such that Q of C is not 0. There's the only caveat. There's the only thing you have to be careful for, that when you take the limit of this, that your denominator does not become 0. Okay? If it does, those values are out of there. Okay? Most of the time. Okay? Numerator, it doesn't matter. Denominator, C cannot produce a 0 value in the denominator. Now, the reason I hesitated there and said most of the time, P and X and Q of X, both being polynomial functions, can be factored. And they have a common factor at X equals C. Then that X equals C in the denominator, Q of C, that factor is disappeared. Okay? And you still can't evaluate the function there, but the limit will exist. It would be whatever it would be of these two, and this is a little abstract here, I know. Whatever would be left over after you factored out the 0 element there in that denominator, whatever it would be if that were not considered, that would be the limit. The function wouldn't have a value there because Q of C would still be 0 if C produced a 0 there. So we'll see an example of that coming up later. Still would have a limit, but the function wouldn't have a value there. And we hit some of those earlier, but we'll see them now. So here's example 3. This is a rational function, ratio of two polynomial functions. All right, question for you. Is there any problem anywhere? Say again? Nowhere? Say again?
There's an X in the denominator.
X in the denominator, and what would be problem with that?
If it was -1.
If that was a -1, you're in deep trouble. Okay? But it's not. X is approaching +1, so there is no problem for this limit here. What would you do? Plug it in, and what does that give you? Not that hard. 1 plus 2 over 1 plus 1. Didn't know you'd be doing such high-level math today, did you? What would this come out being? 4 over 2, which is 2. Done. Okay? 1 plus 1 is 2. Got it? Okay. Remember that for your next test. Okay. Now, any questions on that? No issue here because as X approaches 1, that doesn't mess with your denominator. Numerator will never be a problem with a rational function. The denominator may be, but for this value of X, nope, no problem at all. Okay? So let's see how they did it. Because the denominator is not 0 when X is equal to 1, you can apply theorem 2.3 and get exactly what we did, 4 over 2, which is 2. And then here's the graph of that function, which I know you all wanted to see. This is at least a partial graph of that function. Okay? Does anyone want to make a guess about what the part they didn't show will look like? Say again?
The left side or the right side?
Okay, what you think? I think the right side looks like it's going pretty well there, don't you? Okay. The left side. Say again?
Straight up. Straight up.
Okay. The left side of this is going up, and you guess where it's going up? -1, okay? If they had extended this out and had a -1 here, yeah, that's a vertical asymptote. Never going to get there. Going to approach it, but never touch it. Okay? On the other side of that vertical asymptote, you'll have the function that probably does something like this. Coming up from -infinity, and then, does anyone recall what this would be called? a slant or oblique asymptote. Okay? Anyone remember how you get that? Okay? Do your long division. Okay, actually here you can do synthetic division. And I bet you that's going to come out. Let's just do it quickly. This is just a review. No extra charge for it though. How do you do synthetic division? What do you put outside the house? A -1. Okay, what goes inside the house? 1, 1, 2. Skip a line, draw a line. You probably didn't learn it this way, but if you were in my class, you did. Okay, what does that give you? -1, 0, 0, 2. Okay, what does that represent? Oh, I like always to take that last out. What does that represent? That means x plus 2 over x plus 1. Okay? Now, something seems a little squirrely here.
The whole thing be,
What's that?
wouldn't the whole thing be over x plus 1?
No, you did synthetic division. Right here, the whole thing's over x plus 1, but when you divide it, that gave you x, which would indicate to me the the slant or oblique asymptote was x, and it should be x plus 1, I think. Because that sure looks like that is the the slant asymptote. But this gave you just x. Did I do something wrong in my... I sure don't see it. Okay. Shouldn't have gotten off here anyway, should I? Okay. But that would normally be the slant or the oblique asymptote, and let's just see what this would produce if I plug in x equal 1. 1 plus, that works. So I don't know. Shouldn't have gotten off there anyway. Seems like that should be x plus 1 rather, no, x. Yeah. Not going to worry with it now. Okay, sorry about that. Now, polynomial functions, and back to what I should be doing, and rational functions are two of the three basic types of algebraic functions. Okay? The next theorem deals with the limit of the third type of algebraic function, one that involves a radical. Now, why isn't a radical included in polynomial or rational? What do we mean by radical in a function? Give me a simple example. Square roots, or cube root, or 6th root, or 17th root, or whatever, okay? Now, how do functions look if they have radicals in them? What is different from a polynomial or a rational function? Remember, a rational function? Ratio of two polynomial functions. So basically, you're dealing with polynomial functions versus a radical function. What's the difference there? Little exponents. What's the exponent for a radical function? It could be a square root. What's its exponent that represents that square root? A fraction. Square root would be an exponent of 1/2. The 17th root would be a fractional exponent of 1 over 17. 17th root of something cubed would be 3/17. Okay, so that's the difference here polynomial functions and rational functions, or ratios of polynomial functions, always have positive integral exponents. Okay? This one does not. The radical has a rational exponent. Not rational function, but rational exponent. Now, so here's theorem 2.4. Limit of a function involving a radical. Let n be a positive integer. The limit below is valid for all c's when n is odd. Okay? Hang on to that concept. And is valid for c greater than 0 when n is even. Okay? The limit as x approaches c of the nth root of x is the nth root of c. Again, you just plug it in as long as this makes sense. Now, when does it make sense? Anytime n is an odd number. Remember, n is a positive integer, so it's either going to be positive, or even or odd, right? Only two options for positive integers. If it's a even integer, this is only good when n for positive c's. Because you cannot take square root, the fourth root, the sixth root, or any even root of a negative number. So n has to be, c has to be positive here, okay? Greater than 0. Now actually, it could be 0. There's no problem with taking an even root of 0. It's going to be 0. But they say greater than 0. That's okay. Greater than or equal to actually says it a little better, okay? But if n is an odd number, no problem taking the cube root, fifth root, 17th root of a negative number. That's perfectly okay. You just can't take an even root of a negative number. That has to be non-negative c. All right. So again, we plug it in unless, of course, n is odd, even, and c is negative. Then there's no solution. No limit. The next theorem, do they have enough theorems here? Greatly expands your ability, did you know that, to evaluate limits because it shows how to analyze the limit of a composite function. Y'all remember composite functions? The little circles. F of g of x, g of f of x, composite functions. Limit of composite function. If f and g are both functions such that the limit as x approaches c of g of x is this limit L. That means there is a limit, has a value L. And the limit as x approaches that, L, of f of x is f of L. Okay? That sort of makes sense, doesn't it? This just tells you g has a limit as x approaches c at some value L, but then f also has a limit as x approaches L, and that's the value whatever f of L is. Then, if that's the case, then the limit as x approaches c of f of g of x is, plug it in, plug in the c for the x, that would be f of the limit as x approaches c of g of x, which would be the limit of g of c. The g of c is L, so that would be f of L. Okay? Now they make it sound really convoluted here. You plug it in and see if it works. If g doesn't have a limit when x approaches c, all bets are off. Okay? This will not work. Or if g does have a limit, but f can't be evaluated at that limit, then all bets are off. It doesn't. This will not have a limit. But if both of those conditions are met, you're no problem. Okay? Just plug it in and evaluate. So let's do a couple of these once Andy gets here. Okay. All right. Good deal. Now, let's do the first. Anyone want to make a guess of what this will be? A little louder.
0.
Someone say 2. Sounds like a wiener to me, okay? First, plug this in here. X equals 0. Plug it in here. 0 squared plus 4 is 4. Square root of 4 is 2. Done. Okay. Now, any reason that wasn't plus or minus 2? It's not. This is the principal square root. You would have had to have a plus or minus in front of this for that to be this. No, this is 2. Exactly 2. Okay. How about that next one? Anybody? I'll pull out the calculator. Yes. Second? I don't think so. Let's plug it in and see. That would be the limit. I'm going to write it on out. The limit as x approaches 3. Let's not even mess with that. Let's just plug it in, Okay? This would be the cube root of 2 times 3 squared minus 10. Okay? And what would that give you? The cube root of? Wait, you may have been right. I was not paying attention. Yeah. 3 squared is? 3 squared is? You're absolutely right. It was 2. Okay? That would be 9 times 2 is 18. I was thinking I didn't even notice the 2 or pay any attention to 2. Minus 10, cube root of that, and that would be the cube root of 8. And what is the cube root of 8? 2. Okay. I was not paying attention to the 2. I just plugging in there. What would that one have been? Could you even do it? What would that have given you? Square. What is 3 squared? 9 minus 1. 9 minus 10 is negative 1. Cube root of negative 1. Anybody? Can you do it? Yes, you can. That's an odd exponent. I mean, what do you call it? What's the word for that? Index. That's it. Index. Odd index. You can't take the cube root of a negative 1. What would it be? Negative 1. Exactly. So that's what I was doing. I just knew they were going to give us one with a negative in it since they gave a cube root, but no, they didn't. They gave it also to be 2. All right. Let me, I can do it. The first one, because the limit as x approaches 0, plug it in. That would be 4. All right, wait a minute. All right. Boy, are they making it difficult to see. They're first doing this part, what they were calling the g of x. So they first did the limit as x approaches 0 of the innermost part, which is g of x, and that would be 4, and then take the limit of this. I don't like this way of doing it, okay? Because here x is representing one thing, and here x is representing something else. It's the same problem. So stick with what they give us, okay? But they're showing the g of x here, and then f of, technically they should call it f of y or something else like that. But yeah, get the same answer. But I found the method to be more confusing than it needs to be. Just plug it in, okay? That's what I like, okay? And then you can conclude that the limit of that is 2. Why didn't they conclude that to begin with, okay? I don't know. Sometimes showing all the steps, possible steps, makes it almost more confusing than just doing it. Okay, the second one, not neglecting the 2 there. And again, they're going to start with the innermost function, evaluate that, give you 8. Okay, then plug that into the outermost function. The limit as x approaches 8. You see, this is a different x from this x, so that's why I don't like this. They're giving it the same name here. But as long as they split the problem, I guess that's okay. And that would be the cube root of 8 is 2. Very good. Any questions? All right. Now, you can conclude that the limit as x approaches 3 of cube root of 2x squared root. Just plug it into the x, take this cube root, you get 2. Now, what we just talked about are 3 different forms of algebraic functions. What were those forms? Say again?
Analytic.
Okay, all this is analytic evaluation of limits, but what 3 types of algebraic functions did we just talked about? Polynomial functions, rational functions. It starts with the same 2 letters as rational. Yeah, long hair, radical function. Okay, never mind. Okay, I was from the city. Okay, now those 3 types can be evaluated by direct substitution, as long as you're not going to divide by 0 and you're not going to try to take an even root of a negative number. As long as you don't have those problems, you're in good shape. Now, here's where this text differs from the old text. Did anyone have the old text, which is the calculus without early transcendental functions, the 11th edition? Okay, you have that. Okay. How did you wind up with that? You got it on the Birmingham
I've
calculus.
had it. I've had it for since last semester.
Oh, I see. Yeah, sorry about that. Okay. Stuff we're doing now, okay, if you'll notice in that book, that was chapter 1, what we're in now. Where we're going to jump to here is chapter 5. And you won't have to do all of chapter 5, but you'll find all this in there. Same 2 authors, it's just put together differently. Okay, the basic transcendental functions are trigonometric functions, exponential functions, and logarithmic functions. Now, there's plenty more. Those are the only 3 we're going to deal with, okay, at least for now. They also possess that desirable quantity. Plug it in, plug it in. The only difference is it's the same deal. You have to pay attention to where the functions are not defined. So let's start with the trigonometric functions. Where are they defined? Well, actually, there's 6 different trigonometric functions. What are they? 6 trig functions. Okay, I'm going to have to talk with some trig teachers. Okay. Oops, I was one of them. Okay. Sine, cosine, tangent, cotangent, secant, and cosecant. Okay, do any of them have any difficulties anywhere? Sine. No. Sines are defined everywhere. You will never have an issue with just a plain sine function. How about cosine? Defined everywhere. How about tangent? Anybody? Tangents are defined. The places where they give you problem are at the half pies. Because remember, tangent is, if you think of your unit circle, or even your triangles, it's opposite over adjacent when the adjacent goes to 0, which is at the half pies. Okay? Not defined. Also, secant, not defined, because that's 1 over, or hypotenuse over the adjacent. So anytime you have the adjacent in the denominator, which is tangents and secants, they're not defined there. How about cotangent? Those are the even pies. They're undefined at the whole pies. Oh, I like that sound of that, whole pie, yeah. Okay, that would be 0 pi, 1 pi, 2 pi, 3 pi, negative pi, negative 2 pi. Any of your whole pies, that's where cotangent and also cosecant would be not defined. So those are the only you have to worry about in trigonometric functions. How about exponential functions? All real numbers, no worry at all there. How about logarithmic functions? Any issues there? It's basically the worst of both worlds of rational functions and my brain's not working. Square root functions. Number 1, you cannot take the log of 0. Ever. Ever. Number 2, you can't take the log of a negative number. So logarithms are only good for positive numbers. Square roots are good for non-negative numbers. You can take the square root of 0, but you can't take the log of 0. Okay, so it's sort of both worlds. So, those are the only things you have to do. As long as that's not happening, any of those, then plug it in. No sweat there. So here's what it says. Limits of transcendental functions. Let C be any real number in the domain of the given transcendental function. There's the weasel word. Because C is, if C is negative, it's not in the domain of a log function. If C is pi halves, it's not in the domain of the tangent function. Okay? So as long as C is in the domain of the given transcendental function, then this works. The limit as x approaches C of sine of x is sine of C. Cosine of C. Tangent of C as long as x is in the domain of tangent. That's the caveat. That's good. Sine and cosine, everything's in the domain of that. So no problem there. Cotangent, yes, as long as x is not an even pi, or a whole pi, okay? This as long as x is not any half pi. This is, again, half pies. This is not whole pies. And this one, this is any exponential function, good everywhere. Now, of course, a can't be 0. That has no problem with that. You just don't, exponential functions are only defined when a is positive. When a is 0, it's not even an exponential function, it's a 0 function, okay? And you don't define it when it's negative, okay? So a has to be positive. But that has nothing to do, helps to do with the function. And here, the limit is of log x as x approaches C is C as long as C is not 0 or negative, because that's where not in the domain. Okay, any value x will be in the domain here as long as it is not as positive. Okay, any questions on that? All right. I hate it when they do this. Okay, how would you do that? Plug it in, and what do you get? 0, okay, because the tangent of 0 is 0, okay? Tangent is sine over cosine, sine of 0 is 0, cosine of 0 is 1, so yeah, that's going to be 0. No problem there, okay? How about this one? What's the limit of sine squared of x as x approaches 0? Second?
0.
0 again, because sine squared, I'm so glad they rewrote it this way. No, it's not necessary. Just plug in an x, x equals 0. Sine is defined everywhere. Sine squared is therefore defined everywhere. This is just kind of a composite function of the squaring function and the sine function, okay? So you plug this in, x go to 0, sine of x, sine of 0 is 0, 0 squared is 0. Yeah, no problem there. Okay, how about this one? No. We have a product of a polynomial function and an exponential function. And we got x going to minus 1. What you reckon that's going to do? Does it exist? If so, what's its value? What would you do? Plug it in, what do you get? Okay, negative e to the minus x. Okay? Now they break it down as the product. The limit of a product is the product of the limits. Okay? And this would be a negative 1. This would be an e to the minus x, which is perfectly good because e is defined everywhere, all real numbers. X is defined everywhere, all real numbers, so this would be minus e to the minus x. Perfect. Any questions? Now, anyone want to just give me a general idea about what the value of that is? Roughly. Close to negative 1/3. Because e is a number, 2.7, blah, 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 blah. It's an irrational number, goes on forever. The first two digits are 2.7. So it's pretty close to 3. So this would be something close to negative 1/3. A little bit less than negative 1/3. But who cares? It's just negative 1 over e. Or negative e to the minus 1. All right. How about this one? Ooh, what would that be? Guess what we would do? Plug it in, plug it in. First, is that legal to plug in though? What is E? I just told you. It's a number. What kind of number? Irrational. What kind of irrational number? Positive. Positive irrational number. When you cube it, it stays a positive irrational number. Can you take the log of a positive number? Yes. You just can't take the log of 0 or negative number. So this stays positive, you can do it. So let's do it. What would be your first step? Say again?
Plug it in.
Okay, what would you plug in?
E in place for x.
Okay, and what would that give you?
Ln e to the 3rd power.
Okay, what would that give you? You remember your rules for logarithms?
Pull the 3 out in front.
Pull the 3 out in front, very good. So it'd be 3 times the log of e. And what is the log of e? 1. Exactly. So it'd be 3. Perfect. Okay? A bit easier rather than plugging in first is to use that rule of logarithms there. And, well, I just move it in front here, move it all the way in front. Then plug in the e and log of e. Remember, those are inverse functions of each other. My words are not coming today. Inverse functions of each other. Anytime you take a function of its inverse, you're going to get 1. Always. If it has an inverse, function of an inverse or an inverse of a function is going to be 1. So this is going to be 1. 3 times 1 is 3. A lot of review there, and that one wasn't there. Okay. Any questions? Okay. Is there an E? No. Okay. We made it through example 5. Good for you. Okay. So, what's your strategy for finding limits? I think we've just done it. Okay? You've studied several types of functions, and this, by the way, is why I am leaving that other book behind, because the other book only stopped with algebraic functions in chapter 1, and then went to chapter 5 before they picked up early transcendental functions. You just broke your whole train of thought and everything, so that's why we went to this new book. Okay, you studied several types of functions whose limits can be evaluated by direct substitution. This knowledge, together with the next theorem, can be used to develop a strategy for finding limits. What if you have a function that agrees perfectly fine everywhere except one point? So let C be a real number, any old real number in the world, and let f of x equal g of x for all values of x as long as x is not equal to c. On some open interval that does contain c. So your c is some x value, okay? Well, it's not a value of x, but it's on the x-axis, but x can't be necessarily that value. But this interval contains that value c. If the limit of g of x approaches, as x approaches c exists, then the limit of f of x also exists because they're the same functions everywhere except x equals c. So if one of them is the same as the other one, except at that one point, then the limit, if this one exists, the other one exists. So the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. Okay. Now there's a lot of gimmies in that. Okay. C is any real number, that's not a bad one. F of x equals g of x, that's not hard to comprehend. But it may not be true for x equals c. But everywhere else is true on that open interval containing c. Then if the limit of g of x as x approaches c exists, of course if that doesn't exist, f is not going to exist either. Then the limit of f of x is going to be the limit of g of x. Now that sounds like a lot of weasel words. So let's see what we can do with that. Can we find this limit? Now this is going back to something I told you ahead of time, and you probably is going to taint your mind, but it still works, okay? What would you do here? Plug it in, what do you get?
What's the third minus 1?
It's what? Numerator is? Yeah, 1 to the
third.
Right.
Minus 1.
Which is?
0.
0 over 0. Anything wrong with that picture? Now, I introduced a terminology that works. They haven't introduced it yet. I think they will later. But what did we call that before? Okay. Number one, you can still never divide by 0. But in the old days, if you saw a 0 in the denominator, you'd say, undefined. What did I tell you about this one special case, say? Indeterminate, exactly. If it was 17 over 0, undefined, hang it up, go home, it's not going to work. Never, okay? But if it's 0 over 0, you have to keep digging. So, how could we dig here? What might we try first? There are actually a couple things we can do, but one of them we haven't had yet. So what are we going to do here? Now, for those who've been in my class before, you've probably heard me use this dumb analogy, but I'll use it again. In this class, now if this offends anybody, I won't do it. But in this class, what's going to be the F word? Does anyone remember? Factor, exactly. Okay. Wash your minds if you're thinking anything else. Just go out and scrub them, okay? So, is either of these factorable, numerator or denominator? Did I hear a no? Say again? Numerator is. How is it factorable? Say again?
X plus 1.
No, it's x minus 1. Same sign. then the next part, you change the sign. Okay. When you're doing the sum or the difference of two perfect cubes, x cube's a perfect cube, 1's a perfect cube, right? How that factors is the cube root of the first, x, same sign, minus, cube root of the second, 1. Okay. The second factor is a little more complicated. Forget about this. Let's just focus on this. This is strange, but it works. Square the first, and you get x squared opposite the product of the two. Well, you multiply those two together, you get a negative x. Opposite of that is plus x. And then square the last, plus 1. Okay? You probably don't remember that, do you? Probably wasn't worth it, but guess what? It comes in handy. Okay? So, anytime you have the difference or the sum of two perfect cubes, the first factor, the little factor, the binomial factor, is the cube root of the first minus, same sign, cube root of the second. Okay? Once you have that first factor, then use that to give your trinomial factor. And that's going to be the first factor squared, opposite the product, second factor squared. Every time it works. Okay? Now what you can do is divide by x minus 1. Your denominator there, that can't be factored. And really, technically, we should write the limit as x approaches 1. But what happens here? That's why we factor. They divide out as 1. Now, can you take the limit of what's left as x approaches 1? What do you get?
1 squared plus 1.
Higher level math today, huh? 3. Okay. That's the limit. Now, does that function, that rational function, exist at x equal 1? No, it doesn't. But the limit, and here's the reason why. This is your f of x. This is your g of x. The limit of g of x as x approaches 1 is 3, and these have the same values everywhere except x equal 1. X equal 1, they're not the same. But everywhere else they are, and therefore your last theorem is satisfied, and that limit is 3. I'm probably going to need to erase something, but let's, oh no, maybe not. So, let's let f equal x cubed minus 1 over x minus 1. Okay, fine. Is it time, or do you have to leave early? Okay, all right, good. Okay. Listen up. It'll all be on YouTube. I am recording. I have to check that. The other night, Wednesday, a week ago, I forgot to turn on the recorder. Yeah, okay. Operator error. Okay. So there's your f of x. What we do by factoring and dividing out common factors, you can rewrite f of x as that. That's now your g of x. They're the same everywhere except x equal 1. Not the same there because f is not defined to x equal 1. But g is. So here's the difference. At x equal 1, g is 3. At f equal 1, at x equal 1, f has a hole in the function because it's not defined there. But everywhere else it's the same as that. So this is, y'all don't remember Butch Cassidy and the Sundance Kid, do you? Great movie. If you can find it, watch it. It's Paul Newman and Robert Redford. Fantastic. But there was in that the hole in the wall game. Well, this is the hole in the function game. Okay, never mind. It has nothing to do with it. Okay. But that one has a hole in it because it's not defined at x equal 1. Have to leave a hole. Everywhere else is the same as that. Okay. So the limits are the same. Because, even though it's not defined here, there's no value there, the limit as x approaches 1 from the left-hand side is 3, and the limit as x approaches from the right-hand side is 3. It's just it's not defined at x equal 1. Okay. Make sense? Please say yes. Okay, good. All right. This is still example 6. Because the limit as x approaches 1 of g of x exists, that's the trinomial, the quadratic function, that exists. You can apply theorem 2.7 to conclude that f and g have the same limit at x equals 1. Even though f is not defined there, no problem, but they have the same limit there. And what you do, factor, divide out, and evaluate that, which we just did, and I don't see why they're doing it again, except it's fun to do it again, I guess. Okay, so the same thing there, and that gives you, wow, string it on out here, equal 3, just like we did. So that gives you one strategy for evaluating, finding a limit. If your limit is of indeterminate form, see if you can factor numerator and denominator. Get rid of that problematic value, x equal 1, x approaching 1. If you can, you probably found your limit. Okay? So there's one strategy. Got it? All right. Oh, and here they're going to say that. Learn to recognize which limits can be evaluated by direct substitution. Okay? Guess what? Plug it in, see if you can. Okay? If you come up with just a number, that's probably it. But when the limit of f of x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f for all x's other than that. Okay? They make it sound so hard. Choose a z such that the limit of g of x can be evaluated by direct substitution. Then apply theorem 2.7. Conclude analytically that those limits are the same, and that will be your g of c. Even though f of c is not defined, g of c, if it is, and their value have same value everywhere else, that will be the same. And then, of course, we want to use a graph or a table to reinforce our conclusion. Yeah, right. I do it every time. Okay. If you can get the other to work, it's almost guaranteed. But some of you are rich and have graphing calculators. Plug them in, see what you get. If indeed you get something that they look alike, then yeah, that's probably going to work. So we just done what we call the dividing out technique. Okay? So here we're going to do another one, aren't we? Another procedure for finding a limit analytically is the dividing out technique. That technique involves dividing out common factors. Oh, how new and novel of an approach. Here's example 7. Okay. What would you do first? Second? Plug it in, of course. Good answer. Okay, and if you plug in a -3 here, you get a 9 plus or minus 3. 9 minus 3 is 6. Minus 6 is 0. What do you get in the denominator? Always do the denominator. Don't assume just because the numerator is 0, that may be the answer. What do you get here, down here? 0. No. Well, you got to, yeah. No, okay, wait. That's not -3. This is positive 9. Okay. Minus 3 is a plus 6. Minus 6 is 0. Numerator 0. Denominator, minus 3 plus 3, also 0. Now, if that had come out, a -3 over 0, hang it up. You're never going to get an answer for that. That's an undefined form. No limit exists. But if it comes out 0 over 0, hey, we can run with that. We may fall down, but we can run with it and see if something happens. So what would be your suggestion of what to do next? I'm going to write the limit words in here because I forgot I didn't last time.
Factor. All right. Now what? You remember your factoring techniques? I like to call it unfoiling. Okay. Now you probably never heard of that before because I made it up. Okay. Now, no, I have seen other people use it. What's the only possible factor of x squared? X times x. Okay. So let's put an x here and an x there. Okay. Where do we look next? The sign of the last term. Let's say negative. What does that tell you about these two signs? They've got to be different. One's a plus and one's a minus. That's the only two choices we have. If they're different, we know they've got to be like that. Now, next is, what's the only possible factorization of 6? There's several. 1 and 6, 2 and 3, 3 and 2, and 6 and 1. Okay? Now, so what we want is the factorization that multiplies to be 6. All 4 of them do, but because they're different signs, the difference has to be a 1. Say again, positive 3 and negative 1 is negative 2? Ah, he's got it. Okay. Positive 3 and negative 2. Yeah, 3 and 2, the difference is 1. And when you add those two together, you get a plus 1. And that's what you got here. And then we do what? And guess what? I would have guessed x plus 3 anyway because that's the one I want to get rid of. And if it didn't work, it doesn't work. But that's what I hope it is. And sure enough, what does this give us? Those divide out. That's why they call it the dividing out technique. Very clever the way mathematicians come up with these names. The limit as x approaches negative 3, what do we have left? X minus 2. Now we plug that in, and what do we get? Negative 5. Perfect. Okay? Now, you can't plug that in here and get it to work. Okay? Because negative 5. No, you can't. Why not? No, you can't. That's not what x is equal to. That's your answer. Okay. So, no, you can't plug it in because that's not what you're getting. But that is the limit. Okay? This is example 7. How did they do in the book? Yes, they got it too. Good for them. I'm so proud of them. Okay. Any questions? Want to watch how they did it? Okay. Although you're taking the limit of a rational function, you cannot apply the theorem 2.3 because the limit of the denominator is 0. Okay? Don't just take the limit of the denominator, take the limit of the numerator as well, and that gives you 0 over 0. If that would have given you negative 17/3 over 0, that's not going to work. It'll never work. You hang it up and say no limit. But if you get a 0 over 0, you have to keep plugging. Okay? That's what we've got here. So because the limit of the numerator is also 0, the numerator and denominator, now I don't like that way. Because the limit of the numerator is also 0, the numerator and denominator have a common factor at x plus 3. Maybe that's true, but there's no guarantee it is. Factor and see. And indeed, they do. So for all x's other than negative 3, you can divide out that factor. And that gives you x minus 2. That's your g of x. Remember, x can't be negative 3, but the limit of g of x as x approaches negative 3 will be negative 5. The limit as x approaches negative 3 of x minus 2 will be negative 5. Just like we got. Good deal. Any questions? Beating this in the ground? The result is shown graphically here. What you were all looking to see. Notice the graph of the function coincides with the graph of x, g of x equal x minus 2. The only difference is that there's a hole right there where x is negative 3 and y is negative 5. You got a hole in the function. Otherwise, it's that straight line, which is
g of x equal x minus 2. G of x would be the whole thing, covers that. Your f of x, you have to have a hole there because x cannot equal negative 3. Any question on that? Of course you want to graph it and make sure that's true. Okay. In example 7, direct substitution produce a meaningless fractional form. I don't like meaningless. 0 over 0. Now they finally get around to telling you an expression such as 0 over 0 is called an indeterminate form. Not meaningless. It may have meaning because you cannot, from the form alone, determine the limit. If that was a pi thirds over 0, no, that would not be indeterminate, that would be undefined. But this one is not undefined, it's undeterminate. So when you try to evaluate the limit and encounter this form, remember that you must rewrite the fraction so that the u denominator does not contain a 0. If you get that, you're okay. One way to do this is to divide out the common factors. That's one possible way to do it, okay? Any questions before I move on? Now, they seem to like these little technology pitfalls, okay? And this is showing exactly what I suggested before. If you use a graphing calculator, as long as you miss trying to evaluate x at negative 3, you're going to get a straight line, especially if you're in connect mode. So don't always trust your graphing calculator. If you included x equal negative 3, you're going to get you're going to get some sort of thing like domain error or something like that. So, just because your graphing calculator says that's a straight line with every point in there, if you didn't evaluate it at that point, it's going to connect the dots, and that's what it's going to give you. So the second technique after factor out technique is rationalizing technique. And y'all are good at rationalizing, I know. I could ask your parents, right? And yeah, they cannot rationalize anything like that. We won't go there. Okay. Another way to find a limit analytically is the rationalizing technique, which involves rationalizing either the numerator or the denominator. Now, back when you did this when you had radical expressions, we usually only worried with rationalizing denominators. Here we're going to do whichever one works for us. We know that rationalizing the numerator or denominator means multiplying the numerator and denominator by what? It's conjugate. That's the key. Okay? Of either the numerator or the denominator. For instance, what if we're rationalizing this? Well, why would we even want to rationalize that? Well, they don't. It doesn't matter. Okay? They're just giving you this as an example. This is not one that you would want to do in a limit. Well, the only place this will give you a problem is a limit that x equals 0. Rationalize the numerator is not going to do you a dab of good if you do it, because you're going to have, if x is 0, this is 0, you have 4 over 0. Undefined. You don't mess with it. Okay? But if you did, for some other reason, want to rationalize that numerator, how would you do it? Multiply numerator and denominator by square root of x minus 4. Perfect. Okay? So let's do it. They've done it too. Well, no, they don't show it yet. So let's do that. Okay? Now, notice we don't. Okay. If you had another radical expression down here, you don't multiply, or whatever, you don't multiply by the conjugate of the numerator and the denominator. You multiply the conjugate of the numerator over itself. Why? Why do you have to use the same in both?
That's equal to 1. And when can you multiply by 1? Anytime you want to. It's not going to change the value. So that's what we do here. Now here's what's going to happen. You're going to, in some sense, simplify the numerator. You're going to make the denominator a bigger mess. Okay? That's going to happen. But what do you get in the numerator? Do you need to FOIL it, or do you remember how to do multiply the sum and the difference of the same two numbers? What you get? X minus 16. Perfect. Square the first, square the last, the negative sign in between, because you got minus times plus is minus. Okay? That's your new numerator. Your new denominator is a pain in the neck because it's gotten worse. X onto the square root. Keep making that too big. Okay, let me do a little smaller. Just, yeah. Okay. Now that didn't get you anything at all. It was just showing you how to rationalize the numerator. Okay? It doesn't make anything simpler because there was nothing to simplify here. It's just showing you how to do it. Okay? Now, this one makes more sense. Okay? Here's a limit. Find the limit as x is approaching 0 of this radical expression over x. What do you think we're going to do first? Plug it in, plug it in. What does that give? Which is? Square root of 1 is? 1 minus 1 is? Over? Yes, indeterminate form. If that had given you anything other than 0, the numerator, you just hang it up and say no limit exists. That denominator is 0. But that gives you a 0 over 0. It is an indeterminate form. Now, you can't factor this. That's why I didn't like the way they phrased it before. If you get 0 over 0, then you can factor out. No, you can't. What do you do on this one? What are we going to do? Multiply numerator and denominator by what? Second? A little louder. The square root of x plus 1 I didn't leave enough. Get out of there. Didn't leave enough room. The conjugate of that is the first term, same last term, but with the opposite sign in between. So that's going to be plus 1. Now, if you multiply the numerator by that, guess what you got to do? The denominator by the same thing, okay? X, square root of x plus 1, plus 1, okay? Now, let's go on and do it here. What does that numerator give you? Stomach's growling, sorry. X plus 1 is the first part. Second? Yeah, I can't hear. Okay. What? Okay. Okay. Now, here's what we're. Oh, maybe it would help. I probably should have done this. Put that in parentheses too. Okay. Now here you have an expression multiplied by its conjugate. What was the technique? Square the first, the negative sign, square the last. The square of square root of x plus 1 is x plus 1. What sign do you put? Minus, right? Always minus 1. You see that? Square the radical and you get x plus 1, and then minus 1 times 1 is 1. Okay? We'll come back to that in a moment. And then we'll write this as just x times the square root of x plus 1 plus 1. Okay? Now what does that numerator give you? Say again? Did someone just say x?
Yes.
I thought you did. Okay. So plus 1 minus 1 is 0. So that's going to be x. So this gives you x over x times the square root of x plus 1 plus 1. And what can we do now? Factor out the x's. X over x is 1, right? So this gives us the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And what does that give us? One half. Perfect. Okay, because you plug in a 0 here, x approaching 0, would be the square root of 1, 1 plus 1, 2. That high level math again. Okay? 1 plus 1 over 2. Make sense? Good deal. Okay. And oh, let's see, I'm probably going to have to erase here. Yeah, let me erase. I got by without it before, but now I will. Okay, by direct substitution, you see you have an indeterminate form. Okay? And that means keep trying. If you got negative 3 over 0, quit trying. It's not going to give you anything. But an indeterminate form, keep trying. And since one of those has a radical in them, let's rationalize. Okay? In this case, you can rewrite the fraction by rationalizing the numerator. So here's the rational form. So there we wrote it again, and then rationalize that numerator, because that's where the radical is. So multiply this by this thing plus that thing. Okay? But if you multiply the numerator by it, you've got to multiply the denominator too. Because you have to multiply by 1 to keep from changing the value. And that's a form of 1. Okay? Now, when you're multiplying two conjugates together, you square the first, that gives you x plus 1, minus squaring the second, and that gives you 1. And your denominator, don't multiply these out, please don't. Just multiply them as factors, x times the square root of x plus 1 plus 1. Okay? Now, this x plus 1 minus 1, if you take out the parentheses, the 1 minus 1 goes to 0, and this gives you just x over x times this. And the x's factor out, which is wonderful to happen. That was your problem child. As x goes to 0, your denominator became 0. Now you've just divided it out. So now you plug in and see what you get. That would be 1 over square root of x plus 1 plus 1. Remembering that x can't be 0 because it couldn't before, it still can't. But there's nothing wrong with this now at x equals 0. So now you take the limit of this new function here as x goes to 0. You know this one can't equal 0. This one has no problem plugging in a 0. So when you do that, you get 1 over square root of 1, which is 1 plus 1, which is 2. There we have it again. 1 plus 1 is 2. Still works, okay? Even with a calculator, it works, okay? Any questions? That limit does exist. It's 1/2. The function doesn't have a value at x equals 0, but the limit is x goes to 0 is 1/2. Are they going to show us a graph? Yes, there it is. Okay. Now, I don't know if you're familiar with this. That looks a lot because it wound up being a 1 over a square root function. And that's an inverted square root function of some nature here. But it just has a hole in the graph there because x can't be 0. Okay. But it's approaching 1/2 from the left. It's approaching 1/2 from the right. It has a limit there. Any questions? Make sense? How are we doing time-wise? I didn't bring in my watch. My battery died. 26. We go to 40. Okay, good. All right. Oh, and here they show it on a table. Aren't you glad? I enjoy doing the tables, don't you? That is approaching 0.5 from the left, approaching 0.5 from the right. So we assume the limit is 0.5. All right. Now, that was example 8. Now let's do the squeeze theorem. Not one of my favorites, but it's certainly true. Next theorem concerns the limit of a function that is squeezed between two other functions, each of which has the same limit at a given x value. Okay? So here's your function f, not defined at x equals c. Okay? Here is your function g, which may be defined at x equals c, and a function h, which may be defined. In fact, it has to be defined at x equals c. And you know that for all values x on some interval that does contain c, that the h of x is always less than or equal to your f, and that f is always less than or equal to your g. But if the f and the g has the same, g and the h have the same value at c, even though f may not even be defined at c, but you know this other part is true, then, except at x equals c, then you know that limit for f has to be the same as g and h. This is the pictorial graph of that. Remembering that the f is the only one that's not defined at c. The g and the h both are, but they have the same value at c. Okay? And if the upper condition holds, then f has to have the same limit there. Okay. So there's your squeeze theorem. I'll get it graphically first, and I will show it. Here's the given. H of x is always less than or equal to f of x, and f of x is always less than or equal to g of x for all x's on an open interval containing c, except possibly at c itself. The f may not be defined there, and may not even have a limit. Well, it does have a limit there, so I don't know. And also, not only this has to be true, but the limit as x approaches c of f of x is L, and it's also the limit as g approaches, as x approaches c of g of x. If those two limits are the same, then f has to have that same limit, because if this is true, then f and the limit must be the same as g and h in that limit. Okay. So the squeeze theorem is also called the sandwich theorem if you're hungry, or the pinching theorem if you're mean. No, I should say that. Okay. Now, I don't know why this is on another slide, but they put it on the bottom here. This has nothing to do with these two, except we're going to kind of prove it using the squeeze theorem. But here are three very special limits that you will be using in the future. Not too distant future, by the way. Okay? the limit as x approaches 0 of sine of x over x. Okay, what would be the first thing you would do? Second, plug it in, what would that give you? It's the sine of 0. Whoa. Where's those trig teachers? Sine of 0. It's also 0. This is a 0 over 0 indeterminate form. Okay? Now, they're just telling you this. That's equal to 1. Okay? Now, they're just telling you that's equal to 1. Now, how about this one? As x is going to 0, what's cosine x? It's cosine of 0. One. So this would be 1 minus 1, which is 0 over 0, another indeterminate form. However, this indeterminate form went to 1, this one goes to 0. Okay. I'll try to give you a little bit of rationale for this in just a moment. Okay? Now, here's another one. The limit as x approaches 0 of 1 plus x raised to the 1 over x. That happens to be the definition of the exponential value, the e, the base of our real number system. We think of it as being 10. No, the real base is e. Okay. And just know it. Okay. Now, I'm going to try to, and this may be confusing, hopefully it isn't. Okay? I want a graph for you. Really lousy graph. You know I love graphing, right? Okay. I'm going to graph for you the sine x. Okay? Sine x something like that. Okay? I didn't do the whole function, just near 0. Right? This is what sine does near 0. All right. Now I'm also going to graph for you x. Y is equal to x. That's the identity function. And it basically looks just like that. And you see, very close to 0, this is 1 over itself, right? Okay? And that gives you 1. Okay? Because those are almost the same functions there. Now, there is a reason for this. Okay? We haven't gotten there yet, but we're going to. What we're doing with with limits is how you evaluate your first derivative. Your first derivative basically tells you the slope. So the slope of the sine function here is 1, the slope of the identity function here is 1, and 1 over 1 is 1. So that's the reason. Now, we haven't gotten there yet, but that's it. Now let's look at this one. I'm going to just do it in a different color. Give me a color other than black. Say again? I can't hear.
Green.
Green, okay. Light or dark? Let's do dark, okay? Okay with dark? All right. Now, first I'm going to do the cosine function. It's something like this, and it goes up, it doesn't go down. But all we're interested in is there. That's 1, right? And 1 minus the cosine function is going to be something close to 0, but see 1, there's 1, and 1 minus 0, those are really close to each other, okay? Over 0, well, these are both approaching 0, and that's approaching 0, so sure enough, that limit is 0, because you have 0 over just the number 0, and this one both the 1, which is the horizontal line, and cosine, which is sort of flat there. That's 1 minus 1 is 0 over 0. All the slopes there are 0. Okay? So I don't know if that's satisfying to you. Hopefully it's not. But at least it gives me, this is 1 over 1. That's 1. This is 0 over 0. And in this case, the slopes are 0. They're going to be 0. I can't tell you anything about that except that's the definition of the number E. That's just it. That is its definition. So know these three. Okay? We'll be using them. Big time. Uh-oh. What about this? Find this limit. The limit is x. Do we have time for it? I don't have a watch.
4 minutes.
4 minutes. Let's see if we can get it done. Okay? What would you do first? Plug it in. What's the tangent of 0? Oh, I forgot. Y'all don't know your trig, do you? 0. Okay? You got a 0 over 0 indeterminate form. So guess what we might do next? What's the F word? Factor. Now, the x can't be factored. Let me get out of green. Y'all had me in green. Let me go back to black. Okay? We'll tangent factor. What would it factor as? Oh, that's right. Y'all don't know your trig, do you? It's what? Okay. So that would be, it's called the quotient rule, or quotient identity, or the ratio identity. Sine x over, what is tangent? Over cosine x. That's tangent x. Two of you are in really deep trouble because I know you're a trig teacher. Okay. All right. And this is times 1 over x. Isn't it? The limit as x goes to 0. Now that didn't help things a lot, right? Except now we can rearrange some things here. And this would be the same as the limit as x approaches 0. And let's get the sine x over x together times 1 over cosine x. Is that legal in most states? Okay? Now, what's the limit of this as x goes to 0? That's your last theorem. Sine x over x, 1. Okay? And what's, plug in the other part, what is cosine of 0? Oh, that's right, you don't know your trig, do you? 1, exactly. Okay? So you got 1 times 1 over 1, which is 1. So what's that limit? 1 times 1. 1! All right, good deal. Okay. Let's see if they did it that way. Direct substitution yields the indeterminate form. That doesn't tell you anything except that you can proceed. If you came up with an undefined form, don't proceed. It doesn't exist. This says proceed. So in this one, we're going to change that to tangent is sine over cosine, and 1 over x is 1 over x. But then if you group the sine over x with x, you know that limit is 1. And 1 over cosine x, the limit of cosine x as x goes to 0 is 1. So that would be, they split them up. Limit as x goes to 0 of sine x over x is 1, and the limit as x goes to 0 of 1 over cosine x, just plugging in, is 1. So this gives you 1 times 1 is 1. All right. Good deal. Now, they show it on a graph, and indeed, that's fine. Now, the only problem with this graph is they should have a hole in it right there, shouldn't they? They did it with a graphing calculator, which gave them a technological, what do they call it? Oh goodness, they've done it a couple times. A technology, oh come on. Right down here. There it is. Technology pitfall. And they fell for it into the pit. Okay? That should have a hole in it right there. So the limit is 1. It should be an open circle there at 0. But the limit is 1. Good deal. Oh my goodness, that was the last example. Yeah, but the trouble is, oh, let's see. Yeah, that was example 9. There's one more example. So we'll start next time with example 10, okay, on the bottom half of page 90. So homework exercises here would be any of the odds, 5 through 17. They're all at Calc Chat. 5's at Calc View. 19 or 21, both at Calc Chat. 21's at Calc View. Any of the odds, 23 to 35, they're all at Calc Chat. 25's at Calc View. 37 or 39, both at Calc Chat. 39's at Calc View. 41 to 45, all at Calc Chat. 41's at Calc View. Any of the odds, 47 to 61, they're all at Calc Chat. 53's at Calc View. Any of the odds, 63 to 75, they're all at Calc Chat. 65's at Calc View. 77 to 85, they're all at Calc Chat. 77's at Calc View. 87 to 93, they're all at Calc Chat. 87's at Calc View. Excuse me. 95 should be at Calc Chat. Either 97 or 99 should both be at Calc Chat. 101 should be at Calc Chat. That's an exploring concepts type problem. There's a writing type thing. 103, it should be at Calc Chat. Good old physics problem, free fall. That's page one, number 105 should be at Calc Chat. And let's see, using what you just did there, you can do in 107. It should be at Calc Chat. 109 should be at Calc Chat, finding a function. But then you have some proofs. Any of the odds, 111 through 115 are proofs. If you want to do those, they should be at Calc Chat. You can think about doing 117. It should be at Calc Chat. There's a true-false there, 119. 119 through 123. Several true-false there. They should be at Calc Chat. Proof at 125. It should be at Calc Chat. And there's a graphical reasoning, 127. If you want to do it, you can. Now, we did a bit more than what I think you're still okay. Example 10 we'll pick up next time. And then we'll be through with 2.3 and we'll start on 2.4. Any questions? So today we were all in 2.3. Didn't quite get out. No questions? All right. Hey, isn't it nice? This week we have class 2 days, not just 1. Okay. And this will be your first time to have a 2-day work week, won't it? Yes, okay. I think you were sick one. Okay. Good deal. We'll see you on Wednesday.
Stay easy.
All right, you too. Thanks. Oh.